Welcome, my name is Avery TORREZ, and in this video I will be presenting the research I conducted for the Texas A&M Online Research Experiences for Undergraduate Students. The main goal of this research is to identify and establish an acceptable range of geometries for mesotensile testing. During this O-REU program, I used Abacus, which is a finite element analysis tool, to simulate a series of valid tests and then compared them to a valid test using an ASTM standard for tensile samples. These set of samples that were simulated have altered gauge length, gauge width, thickness, and variations in transitions from grip section to gauge section. Asking yourself, well, what is tensile testing and why is it important? Well, first, let me inform you on the methods of mechanical testing in material science. We have hardness, impact, creep, fatigue, non-destructive, and tensile testing. The testing method in focus for this research is tensile testing. This method utilizes uniaxial tension loading to induce deformation on a given specimen. These specimens can be several different geometries, but the most common is the typical dog bone specimen. The main purpose of tensile testing is to produce data that can then be converted to stress-strain curves. In the figure to the right, the typical dog bone specimen and the stress-strain curve are illustrated. Key points on the stress-strain curves I will be touching on throughout this presentation will be the yield strength and ultimate tensile strength. You also may be wondering what mesotensile testing is and its importance to modern material science research. First off, let me define mesoscale as being an intermediate scale. In this case, it would be the scale between macro and micro. The effect that this desired scale has on this research so far is negligible because Abacus does not deal with units directly, but rather the ratios of the geometries. The real effect of mesotensile testing will not affect research until experimental data to prove findings for Abacus are executed. In the field of tensile testing, this scale is somewhat unknown territory. So establishing a solid set of geometries within a 10% tolerance of the ASTM standard stress strain values would be an extremely helpful tool for advancing research on mesotensile testing. On the left is an SEM micrograph from previous mesotensile tests produced by Jonathan Gigax and Quinn McCulloch of the Los Alamos National Labs and Peter Hoseman of UC Berkeley. In this image, you can see 5 different tensile samples with a 1:1:4 ratio. These samples were loaded in an effort to illustrate the sample's behavior at yield point, onset to necking, and failure. Now let me give you some background information on the standardization of these tests. So the American Society for Testing and Materials defines specific geometries that encapsulate valid tensile tests. On the right, you can see the parameters I used during the simulations. Once I was able to get good results for this ASTM standard, I then began to alter features on the specimen. Here we have the ASTM sample that was simulated through Abacus. The material used to define plasticity, elasticity, and ductile damage behavior was mild steel in this case. In tensile testing, you would typically have a fixture at the bottom and a tension load at the top, pulling until failure. In the following slides, I will be giving a brief explanation of each tensile sample, followed by a stress strain curve graph that was produced. Here we have the stress strain curve for the ASTM standard. I should also note that all the following data sets are in engineering stress and strain. Here we can see that the tensile sample yields at roughly 325 megapascals and then climbs up, and the ultimate tensile strength is roughly at 475. Here we have a sample with a ratio of 1:1:1. This is a cubic gauge section for instances in which you have very little gauge width and length to work with, and a thick sample. Here is a stress strain curve for that 1:1:1 ratio. Here we have consistent yield results in the stress component, but in the strain percentage it is much higher. This is also the case for ultimate tensile strength, as it is 25 megapascals higher. The next sample is a specimen with a ratio of 1:1:4. This sample has a longer gauge length for instances when there is more gauge section to work with. For the stress strain curve of this sample, we have almost identical yielding to the ASTM standard, but ultimate tensile strength is slightly lower. The next sample is a specimen with a ratio of 1:1:4. This sample has a longer gauge length for instances when there is more gauge section to work with. For the stress strain curve of this sample, we have almost identical yielding to the ASTM standard, but ultimate tensile strength is slightly lower. This next sample has a ratio of 1 to 4 to 4. This sample is thin with a square gauge section. In the stress strain curve for this sample, yielding occurs at a higher strain percentage, but ultimate tensile strength occurs at a much smaller strain percentage. This next sample is a variation of the ASTM standard. On this specimen, I decreased the radius cutout by 50%. On this stress strain curve for this sample, we can see that yielding up to ultimate tensile strength is almost identical, but failure occurs much sooner in the strain percentage. This next sample is also a variation of the ASTM standard, but instead of a radial cutout, we have a sharp angle transition from the grip section to the gauge section. In this stress strain curve for this sample, we can see that yielding and ultimate tensile strength is practically identical, similar to the 50% decrease in radial cutout. The major difference between this and the radial cutout of 50% is that this specimen fails much more realistic to the ASTM standard. And last but not least, we have the sample ratio with 4 to 1 to 4. This specimen has the same dimensions as the 1 to 1 to 4 ratio, but with a thickness 4 times larger, for instances where we are dealing with films or sheets that are very thick. In this stress strain curve for the 4 to 1 to 4 ratio, we can see that yielding and ultimate tensile strength are pretty similar to the ASTM standard. Here we have two graphs comparing the worst and best matching stress strain curves to the ASTM standard. On the top we have the worst matching. Here we can see that the only one that matched up relatively close to the yield point was the ASTM standard variation with half of the radial cutout. The other two ratios, 1 to 1 to 1 and 1 to 4 to 4, were much higher in the strain percent. We can also see that the ultimate tensile strength was only matched up well with the 1 to 1 to 1, as the 1 to 4 to 4 and the ASTM standard variation with half radial cutout is much lower in the strain percent. As for the best matching results, we have 4 samples that are relatively close to the ASTM standard. Here we can see that the yield points on all of the graphs are within 5% strain. We can also see the ultimate tensile strengths in all of these samples were similar to the ASTM standard. In conclusion, there were 4 strong similarities between the ASTM standard for the geometry ratios of 1 to 1 to 4, 1 to 1 to 2, 4 to 1 to 4, and the sharp cutout version of the ASTM standard. There were a few flaws in the stress strain curves, such as slightly lower ultimate tensile strength and lower strain fractures. If these findings through Abacus are proved through experimentation, then I believe these previously stated geometries create excellent guidelines to establish a more suitable set of geometries to effectively gather data for mesotensile testing on materials with properties similar to mild steel. In an effort to expand the field of mesotensile testing, more complex materials, such as composite materials, will be introduced into the same process of establishing suitable geometries. There is also high consideration in attempting high strain rate tests following the same method.